For our final discussion about ions, we want to talk about what are called polyatomics. All right, so polyatomic ions, if we look at this name, it's an ion, so it's charged. This is not a neutral object. But we can see this is different than the other ions we've looked at because it is polyatomic. So atoms, right? We know it's made of atoms. That's good. Ions made of atoms. But poly means many. Looking at the periodic table previously, we've been predicting what types of ions individual atoms would form. We're now looking at poly, which means many atoms. So previously, everything we've talked about have been monoatomic, mono meaning one. So single atom ions. We are now going to look at ions that are made of more than one atom. Okay, so these are atoms composed of more than one atom. They are polyatomic. Functionally, more than one atom combined together is a molecule. So polyatomic ions are molecules that are charged. So there are multiple atoms that come together into a molecule, and that is charged. So for example, there's a polyatomic ion called hydroxide. Hydroxide has the molecular formula OH. It is one oxygen atom and one hydrogen atom. They are together in a molecule. Two different atoms, so we link them together. The entire charge of that molecule is -1. So you can see we put that charge up as the superscript, right? Like an exponent would be, and it's at the end of the entire formula. Okay, it's not on the oxygen or the hydrogen, it's on the whole molecule. So what that means to have a charge is that the entire molecule is negatively charged by 1. There is 1 extra electron for the entire molecule. It's not on a particular atom in this molecule, it's in the whole thing. Okay, so oxygen would have 8 protons, hydrogen has 1 proton. Those are the atomic numbers of those individual atoms. So collectively they have 9. Okay, so this molecule has 1 extra electron because it's negatively charged, meaning there are 10 total electrons in the entire molecule. They're spread out, they're shared by all the atoms, and there's not necessarily one atom that negative charge is on. When it comes to the polyatomic ions, they are just something you need to know, unfortunately. Polyatomic ions, there are some patterns that we'll talk about here, but at the end of the day, you're just going to want to learn what they are. Now, obviously, we're remote, so you can, I'll tell you, you want to learn them. It'll be in your interest to memorize these ions, but you can always use resources to your advantage. I can't, not allow you to do that. But you want to learn these and recognize them. One of the things you will note is that most of these are anions, right? There's a lot of polyatomic anions. There's only one polyatomic cation. So if you think about it, we said we haven't quite gotten there. We'll get there tomorrow. Cations and anions are required for ionic compounds. I have one choice for an ionic cation, polyatomic cation, ammonium at NH4+. It's going to behoove you to learn that. To learn ammonium, because that is going to come up a lot. There's a reason we're learning just that one. Others exist, but they're much less common. That one's very useful. It'll come up again multiple times this semester. And so we really want to get comfortable. But again, these just have names, and those names correspond to formulas. So you just want to learn what they are and be able to pick them up. And we want to, one of the things is sometimes when you just see that name, you want to kind of pick up the fact that you even can look up what the formula is, or recognizing these formulas won't always be by themselves. They'll be kind of packed in with other things, picking out that you're looking at a polyatomic. You don't want to just rely on always looking it up. You want to be able to know and recognize that it's something you can look up. These are the ones that I'm going to expect you to know. There's a slightly different chart in your book that also talks about related acids. We're not going to go into that. I just want you to know, in this case, name, formula, and charge. And there's some kind of tips and some guidelines that we can use to learn those things. One of the things you'll see right away is that they're mostly anions, and a lot of them contain oxygen. A lot of those anions contain oxygen atoms. So those are called oxyanions. because they have the base form of basically some sort of atom that's not oxygen plus some oxygen. 1, 2, 3, 4 oxygens, however many they have. For a given base atom, for example, chlorine, you will see that all of the anions have the same charge. All of these over here, we can see perchlorate, chlorate, chlorite, hypochlorite, all have a charge of -1 because they all have the same base atom of chlorine. Okay? The only difference between them is the number of oxygen atoms. Okay? And so those number of oxygen atoms we can then pick out. So there's a couple rules. You will see one of the rules is that 8 means that it has one more oxygen than ite. So this gets to one of our first distinctions. If you have an ion that ends in ATE or ITE, that has to be a polyatomic. Because if you remember, the ending for monoatomics was IDE. Okay, so ATE and ITE always correspond to polyatomics. Unfortunately, because this is chemistry and we got to make life hard, IDE does show up in our polyatomics. Okay, basically, because historically people thought those were elements. So that is an issue, but it does work. So IDE isn't 100%, but ATE and ITE 100% of the time means you're dealing with a polyatomic. Okay, and if you have ATE, you can see chlorate has 3, chlorite has 2. So if you just learn 8 chlorate, 3 oxygens, you can learn chlor is -1. You can learn that chlorate is 3 oxygens. Then ite has to be 2 oxygens. Additionally, per means like hyper, so it has 1 extra, so you get to 4. Hypo means like hypothermia, it's cold, it's below. That means you only have the 1 oxygen. So those rules are always the case. 8 always has 1 more than the ite, and per has an extra on top of 8, and hypo has 1 below ite. So it's always per 8, then just the 8, then the ite, and then hypo with the ite. Do want to be careful. 8, that ending on 8 is not always 3 oxygens. If you look at sulfate, you can see that is a nice 4 oxygens on sulfate. So it can be tempting when we see like the chlorates and the nitrates that the 3 oxygens would mean 8. That's not true. Sulfate has 4 oxygens. The pattern is 8 and ite is always that difference by 1, but there's not necessarily any restrictions on how many oxygens there are in the 8, in the ATE one. Generally, the ATE one just corresponds to the most common one, is where that comes from. And so that's really the main motivation. The one other nuance to these polyatomics is sometimes with that oxyanion base, you add hydrogens to the front. And so one of the most common places where we see this, the only one we really, one of the main ones we deal with is with respect to phosphate. So phosphate is PO4 3-, we can see right there. And then you can see there is hydrogen phosphate with the 1 hydrogen. And then there is the dihydrogen phosphate, which means 2. And so the di means you have 2 hydrogens. Hydrogen phosphate, just a single hydrogen. Dihydrogen phosphate has 2 hydrogens. Okay, and so we can see similarly, this also works out with hydrogen carbonate and hydrogen sulfate. And so every time you see that word hydrogen, which means you have an extra hydrogen, and that also does affect the charge of the ion. So changing, as long as it was, kind of chlorine, it was always 1-. If there's a P as the base, it's always going to be 3-, but the hydrogens affect that. Each hydrogen, basically every time you add a hydrogen, you add +1 to the charge. So we can see the steps here where it was -3, then -2, and then finally -1 when we added those hydrogens. So we're just adding in a +1 and a +1 each time we add a hydrogen. So when it comes to polyatomics, again, I highly encourage you, use some flashcards, use resources like that help you learn these for the main reason that it's just going to be useful to be able to parse these out. I can't control your testing environment, but when they're kind of hidden in names, you want to be able to parse out. One of the most useful things is remembering that ending, ATE and ITE means it's a polyatomic for always, right? That is always going to be the case and always going to be useful for you to pick that out. And then knowing that you can look them up is really going to suit it. And then ammonium. Don't forget about ammonium. I guarantee you it's going to come up. It comes up as we talk about other topics. When we're talking about naming, I'll use it. When we're talking about making compounds, working with ions, I promise you I'm going to use it.